I'm just going to get started on this thing. So we got, so there's a paper called nucleation. So similar to what we had, let's see, let me go back. Let's see, I'll go back to surfaces like this. Or something. Right, this. So, so I went through. So this is to calculate the critical phase size. So this is the energy change from going from like say you're precipitating a crystalline from a liquid. So that's a change in energy between the liquid and the solid, or it could be vapor and liquid. It could be anything where you're coming out with a 3D structure that's got a 2D surface. Let's say R cubed, R squared. And then if you take the derivative of that and set it to 0, you can solve. So you have like an R squared and an R term. So the R cancels, just have R equals something. That's the magic point where you have 0 slope, you have a maximum in that curve. So the surface energy is bad, and it increases the free energy change. So there's a penalty to making surface, and this is what drives the phase separation. Is delta G is going to be the free energy expression, like the Hildebrand expression. So anyway, that's the standard model that Gibbs came up with to solve for this kind of energy barrier to formation of nuclei. If you form a nuclei that's very small, and then if it grows larger, it's an uphill in energy, so that's a bad thing. So it'll always get smaller. So small nuclei will decay. If you have a large nuclei, it'll always grow larger because it reduces the free energy. So you get a more negative free energy change. And then there's a critical point below which phases will dissolve and above which they grow. And that, because this delta G is temperature dependent, that the height of that barrier and the position of it, the critical size, both depend on the temperature. So you can change by a deep quenching, get smaller phases. That's one thing you can get from this. So this is kind of the Gibbs model for nucleation. So this is a model for nucleation of anything, of a bubble when it boils, or a rain droplet when it forms, or a crystalline phase when it forms, or a liquid phase. When it any phase that forms on another phase is going to follow this rule. Right. And then the other thing was that that's where homogeneous nucleation, like a phase just appears out of nothing. You have a liquid phase, then a solid phase just grows out of that. The other case is if you have dirt in the system and you get heterogeneous nucleation, so you form a platelet on top of a surface. So the only part that changes is kind of the side of it. So it's just the circumference of that, say it's a disk, times the thickness of the plate that forms. And the volumetric part is the thickness times R squared for the area. So the area times the thickness gives the volume. So that's heterogeneous. When you do that, find out you get half the size. So you get a much smaller phases are stable, and the free energy barrier, this barrier peak, is much smaller. So basically, it's much easier to make a heterogeneous nuclei than a homogeneous nuclei. So that's what I went through before. And in this paper, he's following along those same lines. Okay, so you have the difference is he's looking at a grain boundary. So you have if you have two crystalline, so if you take corrugated iron, and you can see like grains in it, or aluminum sheets. Sometimes you see crystalline grains. They can be centimeters in size, right? So, so basically, in normal cases, you crystallize a metal, and it's got crystallized some kind of nuclei, and they grow, and you have with this grain boundary. So it's going to have these grain boundaries in it, and it's crystalline. So it's, you have just one nucleation site, and you can form a perfect crystal. But when they, you have a bunch of them growing in a bulk material, you get grain boundaries. And so he's talking about a grain boundary that's, we have two phases. In this case, they're both BCC phase. And then there's a disclination. So somehow this would be like a BCC crystal. This is like the 110 planes. And then this disclination line, which is a grain boundary, something happens here. So he's talking about what happens at the grain boundary. And he's in this paper, they're talking about two phases can occur at that grain boundary. So he's got an alpha phase and a beta phase. And the two phases, so he's doing computer simulation of this to try to talk about this same kind of phenomenon, like those, in other words, within that two grain boundary, he's going to have a nucleation event. So you can talk about that area. You can have another, so you can have different kinds of phases, different kinds of crystalline. They're not crystalline because it's 2D. So it has some other kind of phase, like alpha forming, and he's got beta forming. And it's all at this interface. Right, so he's talking about that. He can use this nucleation and growth model to talk about that interface. Okay, so that's a map. You can see like the crystal planes going this way, crystal planes going that way. At that interface, the two crystals are in coincidence. So an atom could be in both crystal phase, both crystals. They're the same phase. The top and bottom are BCC tungsten, but the atoms can be in both at the interface. So there's a region of somehow different material at the gap that's got a thickness T. Then he's forming these phases, which should have size. Sometimes he calls it L, sometimes he calls it R. So basically there's a size of a nucleating phase at that. And the black and red he shows in the simulation, they're going to be like this. So you see it's like triangle, 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 space, triangle, 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 space, triangle, 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 space. Right, so that's the alpha phase. And the beta phase is triangle, triangle, and then weird circle, triangle, triangle, weird circle. Right, so these are and you can see the lines are coming down like that, and they go like that. So that's a point of disclination between the two. Right, and that's a grain boundary. And then at the interface, right at the grain boundary, the atoms coincide with that crystal, and these coincide with that crystal, but they form a different structure right at the grain boundary. It's like 2 atoms thick. Right, so that's the thing that he's calling a phase. And he's saying that phase can have 2 forms: this triangle, triangle, 3 triangle space, 3 triangle space, or 2 triangle circle phase, right? Alpha and beta. So he's using the crystalline nomenclature to talk about something that's a little bit different than a crystal. It's confined to an interface. It's a thickness T. It's the same thickness in both. And then he's changing these phases. And he wants to see if he can get this kind of nucleation event going on, where he can nucleate a phase there. So of these 2 phases, they have different energy. So the energy, so he's going to write that same Gibbs equation that I showed you. So this is his Gibbs equation. Instead of R cubed, it's got R squared. Instead of R squared, it's got R. So this gamma is kind of the bulk free energy, but it's actually a surface free energy. And then this is like a line free energy, which he calls the interfacial free energy. So it's the same as what we had in the notes for the homogeneous nucleation. We have bulk and then surface energy, bulk energy. Right? So this bulk energy he can't exactly measure, right? And this because, well, he's going to have a different approach to this thing. So because it's confined to this phase, it's going to have residual stresses in it. So he's got these 3 kind of residual stresses in this thing. elastic contributions of the free energy. In other words, you have to distort. So you have to kind of distort the crystal phases when you get near to that interfacial grain boundary region, which leads to an elastic strain around it. You can calculate the elastic strain by saying he's got this curvature, and then it's got these forces. The F is the forces that are involved, and you can calculate the elastic strains involved in that. So you can add in these three kinds of elastic strains. So three kinds, let's see. So one is the self energy, the loop energy, and the cross energy, line energy. So the self energy, line energy, self energy of the loop. In other words, the bending, kind of the shape of the thing gives it a strain. And then the line force is the force he's tracing along this surface. So he's got this surface, and there's a force that's kind of a torsional force that's caused because he's forcing this triangle, triangle, circle phase into the triangle, triangle, triangle space phase, or the other way around. This is triangle, triangle, circles, beta, and alpha is a triple triangle space thing. Right, so there's going to be a net force that acts along the surface of the interface that leads to these strains. So there's a force of the one phase, force of the other phase, and then a cross term, the force of the two sides meeting. So those strains he can calculate. He's sorted out how to calculate that with these equations that include like the Poisson ratio, the Burgess vector, which is there's a vector associated with disclinations. So basically it's a vector where you have two crystallographic phases don't exactly meet. So at that point, there's a vector that connects the two crystallographic phases together. So these are Burgess vectors for the disclination, and that's the B's here. And then rho is the radius. Rho is the radius of the phase that's forming. And then he adds in these other terms. C are the elastic terms that don't depend on L. So those are extra torsional terms in the structure. And then gamma is another energy term that he puts in that has to do with these. So anyway, he defines with some equation this kind of strain energies that happen at this interface. So it's kind of complicated. I mean, it looks complicated here, and if you go to the supplemental file, it gets even more complicated because it's got a lot of equations to talk about how to calculate those strain energies in the system, right? But in the end, he's got an equation that's similar to what we did in the notes, and the theme of it is going to be the same thing. That he wants to take the derivative of it. Let's see, take the derivative of that, set it to 0, find the peak. That's your critical size. Plug in the critical size back in the original equation, get the critical energy for the transition, right? And in this case, the transition is going to be nucleation of a phase at the grain boundary. So he's talking about this grain boundary as if it was a bulk phase. And then he's talking about that you could nucleate phases within that. So the importance of this is that also the mechanical properties of a polycrystalline metal like that, right? So the bulk crystals are just going to have the modulus of the crystal, right? And tungsten has a BCC crystal, and so it's got symmetry, like the modulus is the same in all the directions. Tungsten. Right? It's also 1.7 times the density of lead. Tungsten's got this some kind of weird things for it. It's extremely dense. So anyway, so if you pull on this bulk polycrystalline material, all the action is at the grain boundaries because this is just a perfect crystal. But maybe it's going to be like 100 micron size, something pretty large. Right? So all the mechanicals of the system are going to depend on that grain boundary. Every property you get out of it, conductivity, Everything's going to just depend on the grain boundaries. So people in metallurgy are interested in the grain boundaries, like to predict the properties, because there's not all the action is at the grain boundary. It's not nothing else. Everything else is just down to an atom. It's uniform from an atom to macroscopic. It's uniform. Then you have the grain boundaries that kind of decide the properties of the material. That's why they're interested in this grain boundary thing. What can happen in it? So the weird thing is that you have. He mentions this in the paper that you have, so he's calculated, or by hook or crook, he's gotten the energies of these phases, the alpha and beta, which are these two phases. And the energies aren't the same. So the lower energy phase is the alpha, and then you have these stresses, tau 1, tau 2, that are the force balances in this thing. So you're balancing off these stresses that are in it, and he calculates 3 forces that arise from the difference in the taus. Right? So he's got this force terms that he puts into these elastic terms. So the force is within the E's here, and the E's are down here, and somewhere in here is the force. Here's the force F1, F1. So he's got the force to calculate these stresses that are on the material. Forces being like, because they don't pack the same, there's some stress in this, right? And there's also a stress because you're inserting something into the two materials. It creates a stress, which is in this circle thing. It's kind of talking about this circular stress. So this is a top view of this disk-like alpha phase within a beta. So the higher energy ones is the thing, and then you want to form an alpha in it. So that's the condition he wants to get. He wants to get homogeneous nucleation within that interface that forms this alpha phase, which is lower energy. All right, so you have a high energy interface. A lot of times the high energy interface, I mean, high energy phases, crystallographic phases tend to form because they're like, if you have a liquid going to crystal, the high energy crystal is closer energy to liquid than the low energy crystal. So it's easier for it to jump from liquid to the high energy crystal. And you get a crystal transition to the low energy crystal. So that you have 2 nucleation events. One is the high energy, like the beta phase would form in a liquid. And then afterwards, after annealing, then the alpha phase would appear within the beta phase to reach the equilibrium lowest energy state. Right. So that's the general idea he's doing here also with this interfacial problem. So anyway, he wants to see that. And what he finds out is that you can make the beta phase and it never transitions to alpha, like no matter what he does, unless he plays around with the thickness and makes the thickness so thin that those stresses become so high, it destabilizes the beta, and then he can get the alpha to form. So he has to really go around, like bend backwards to get this thing to form. So there's two, say the metastable beta function. A is quasi 2D. All right, he goes to a thing where he makes it so thin that it's basically 2D. Like in other words, it's not a 3D film anymore. It's got just atoms, like a few atoms to be the thickness of it. And in that case, he can get nucleation, but the critical size he gets by doing the derivative of the free energy is like really small, like 1 angstrom, because it's 1 atom. So he's getting a phase that's so small it's not really a phase, right? And then when he goes to the thicker films, he gets a larger size. He gets something more reasonable, like 50 nanometers phase, and then he's got about the same barrier energies, like 1, and then this thing's like 1.5 when he goes to a thicker one. So this is like a thin crystal and a thick crystal. Both of them show a critical point, so they're following the Gibbs theory for nucleation. But he can only get these when he tunes the properties of this just right to get this nucleation event going on. So he talks about that in here. I mean, this is a case where, so he's got the beta phase, so triangle, triangle, circle, and he wants to make the alpha phase 3 triangles in a space like this one, right? Repeating. So, but it doesn't form. Like he starts at 0 nanoseconds, he has a nuclei, but the nuclei disappears, just like, so that's basically like he's over here with a small phase forming, it decays because as you make the phase larger, it increases the free energy, and you want to decrease the free energy, so it won't do it. But when you get to a large phase over here, that one grows. So he has a larger phase growing in it. That one phase separates. So he gets all alpha. All the beta turns into alpha. So it's kind of a nice thing. It's got this was so a lot of times in physics they're publishing papers online before it's reviewed. And that's what this is. And then this was eventually published in 2022. Let's see. And then the paper that published, which is the same thing as that paper, but this thing has like 40 citations, which is pretty good, like in 2 years. So that's like a pretty high citation. So this is, despite being a little complicated, it's a popular thing. So anyway, so what else? So that's about it for this thing. That's kind of what's going on. So this idea of elastic, he talks about these at the beginning, this Eshelby inclusion. So it's like when you calculate the energy, if you have a composite that's got dirt in it, some kind of thing in it that's interfering with the crystal structure, so you end up with these strain fields that show up. So this is where he's getting the idea of adding in the strain energy to the free energy. And then this idea of dislocation, strain fields, kind of the same thing. So when you have a dislocation, which there's pictures of it online. Search for it itself. This is probably not here. Oh, yeah, so basically dislocation means you've shifted the crystal structure, so you've introduced this kind of defect. And basically the Burgess vector is the direction that you shifted it. And then this leads to a strain field. This thing just shows kind of what strains you can get from that. Right. So the idea that you're introducing strains into a crystal structure, he's using those two things to talk about that. That's what those two things are here. And then so he's borrowing that idea and he's introducing it into this situation where he doesn't have a disclination, he's got a grain boundary. And basically he's saying he has strains at that associated with inserting this interfacial region that looks like that. So he's doing a computer simulation of it. He's got some of the parameters using tungsten, and then he's doing simulations to get the other numbers. Like he gets, so he does a molecular static simulation to get this lambda term. The gamma term he can't get. The lambda term and these strain energies he gets from a static. So it's basically like a calculation. So he just puts the atoms in that position and does an energy calculation of all the atoms in the system, and it spits out those energies. So there's no simulation to it, it's just a calculation. So he gets some of the parameters from a kind of a molecular calculation. Again, he's using that, I think I mentioned before, that LAMPS program, which is like a generic, it's made at Sandia National Lab, and you can, I think in one of the last chapters, we'll do a LAMP simulation of some surfactants, something simple, but basically you can do crystal, you can do anything with it. And this software, you can just download it and run it on your PC. It's not that hard to use, but, and also because it's so popular, you can just Google whatever problem you have, you can Google and you can find code or script that people have written for whatever you're doing. Like basically, like you could just, like if you just said like lamps and grain boundary energy, something like that, right? And you probably find lamps tutorial on grain boundary energy. It has the code. It'll step you through how to do it. Like you can, I mean, it might take you a couple of weeks, but basically you could do this yourself with no problem. Everything's free. it'll come out with basically what he's, something like what he's got, you know. So this is like basically whatever you're doing, like that's really easy to do, and it puts a lot of kind of science flash in front of whatever you're doing. You can solve things. Hopefully the answer is like logical to you, and then then you can say, well, the lamp showed that, then everyone will agree. If it's not what you thought it was, that's where problems come up, right? So anyway, it's useful. You can get a color graphic of like if you did like, you can probably find video of lamps, simulation of grain boundaries. I bet there's like a video of it, like someone did that. I mean, you end up with a movie. This is the same thing. It was like a nucleus. This is almost exactly the same thing, right? He's making a different phase nucleus here. And is it growing or not? It might even be the same people. I don't know who did this. Anyway, so you can see, like, you can do something fancy that people will watch if you do. Lamps is pretty easy to do. Anyway, so that's that business. So he's all right. There's a bunch of things with this, right? Like, I mean, he's calling this a phase, number one. Like, so I mean, triangles and circles, is that a phase or not? That's something you could ask yourself. Like, all right, you can read this and skim through it and just go, okay, that's great. Like that, it worked. He showed that it worked. He got this nucleation event, and then he showed that that nucleation event was real because when you tried to grow it too small, it didn't grow big, it grew, right? So it's following the classic nucleation behavior. So that's good. But then, I mean, if you start to think about it a little bit, and he's using a bulk equation for the nucleation, right? Notice he doesn't have a surface, right? He doesn't have a surface that he's nucleating that. It's not heterogeneous nucleation, it's homogeneous. But it's all occurring at a surface, or at an interface between two phases, which means it must be heterogeneous nucleation, right? So it couldn't be homogeneous if you're at an interface. So, and the difference is bulk versus surface, and he's all doing surface, but he calls it bulk. So that's a little bit of a twist. Is that a phase or not? That's a pretty big twist. Like, how can you call something like that a phase? You know, and can you have a phase in 2D? I mean, all right, there's a lot to phases in 2D, like with the surfactants. Okay, so if you have with the surfactant, you can have, so you have water, you have oil, and you have a surfactant in between. So the head group is polar, the tail group is like a wax, and it goes into the oil. And so those things will go like that. So you can line those up in what's called a linear trough. Right? You take a kind of a paddle, a wall, and squish those things together. So when they're loose and they have a lot of motion in them, they're like a liquid. And when they get tighter, then they form a crystal. Right? So you can have a phase transition from liquid to crystal by the pressure. It's like a surface pressure, as if you're going through pressure with a vapor or with a liquid to a crystal by putting pressure on it. Right? That's a 2D phase transition. And so you can do that. This has some kind of similarities to that in a sense, except that these things aren't really atoms, and then they aren't really a crystal, and they aren't really a phase. So all they are is like a mess, right? And he's kind of, if he hadn't drawn it red and black, you would not see anything here, right? Because see, you're going down this crystal, and then you get that one's in that crystal. Then you go, boom, that one's in that crystal, right? So there's a grain boundary along here. There's no phase. It's like that one and that one, right? So the phase is just a figment of his drawing capability. I mean, you can look at it that way, like it doesn't exist, right? There is no phase. The phase kind of has to occupy some space, maybe, you know, this doesn't really, this is like that one, then that one, and this. So, I mean, they both do the same thing, but depending on how you draw the circles. And so is there an enthalpy of transition between those two phases? Well, he's calculated that anyway, there's a lot you could ask about this beyond just like accepting it, okay? Like there's a lot of questions about, is this just a game he's playing? Like the energy difference is almost nothing. he comes up with these stress differences. So, I mean, you have to actually like start to question what people are doing, you know. So anyway, 20, 30, 40 citations is pretty good. So people seem to have accepted this. That doesn't mean it's, you know, true. I mean, you kind of have to think about it. I mean, the cartoons look good, but if you look at it, so it should be continuous, right? You shouldn't have like a gap where it isn't phase uh, beta or phase alpha. There's this gap here. What's that? That's like phase gamma, you know, or what? Or is that a liquid phase in between? Or like, there's some kind of questions about what's going on with this whole thing. I mean, you can find sequences, or if you just randomly took this and put it anywhere in the material, could you find three triangles in a space? Like, could you just construct that? You know, so you know, there's questions about what's going on, like from a kind of basic level, like is it true or not? Anyway, it's interesting. I think it's interesting to look at. And it's kind of dense, and hopefully what you can do is like take this stuff. If you know this, so you're gonna have to look at this, and then you can go back to this and you can piece together what he's doing. It's a PRL, so it's a letter. It should be just 3 pages. So it's just a really short paper. But I mean, when people do that, they get around that by having a supplemental file, right? So you have the supplemental is like a lot of pages, like it's, I don't know how many, but you can see it goes on longer than the paper. There are 12 pages of supplemental and 3 pages of paper, right? So it's basically kind of a cheat in a sense. And as times goes by, so a 3-page paper gets a lot more citations than a 20-page paper. So as time goes by, everyone's publishing 3-page papers, and they have a 50-page supplemental. Like you'll see these Nature papers are 3 pages, and the supplemental is like a book, you know. So and it gets published at the same time, so they get credit for the whole thing. They get a lot more citations because, I mean, would you read a 50-page paper? No. But would you read a 3-page? Maybe, you know, it's like you're going to get cited more if you could put the highlights in a little paper. So that's kind of the game people are doing here. Anyway, so it's kind of mathy, but hopefully the idea is like to have you pick through and not get shocked by the math. Like, oh, there's a lot of equations, I give up. So I want you to kind of say like his fundamental equation, the first one, this is the same as the Gibbs equation for phase behavior, and even says like it's a classic CNT is a classic something, classic nucleation theory, which is Gibbs. You might as well call it the Gibbs theory. And then he's added on these other terms. So what else? Let's see. All right, so it isn't just him that's got this idea about phases at grain boundaries. So that people talk about sluggish transitions, time temperature transitions, so that so time temperature is something you get when you have polymers. They talk about time temperature superpositions. When you have an entropic, behavior influencing the enthalpic transition. So in other words, this isn't really a phase. It's like this got disorder in it, and that's causing this time. So if the transition would happen at a high temperature, it happens fast. Low temperature, it happens slow. And there's differences. But the time scale of the transitions dependent on the temperature. He calls the time temperature dependent. So it's got something to do with this business. He's talking about these strains showing up and how the strains are not the normal enthalpic things that are going on with these, so that leads to this time temperature. And then anyway, let's see. The equation, what else do I have here? So again, yeah, he's using lamps for, which is a molecular dynamics. So they call it molecular dynamics, but basically it's a bead dynamic. So if you put so it's a bunch of balls that have an interaction potential with each other, right? An interaction potential is like Leonard Jones potential that has atomic features to it. And then you give it kinetics of an atom moving around, like the diffusion coefficient in atoms. So in that sense, it's molecular. But you could also just put in any kind of potentials and interactions that you want. Then you could be talking about surfactant molecules that are, 50,000 grams per mole at things. Or you can almost do like anything that's driven by KTs, anything like vesicles that are microns in size, or dust in the air or something. So you can do LAMMPS as a molecular dynamic simulation. We can simulate anything that lives by KT. It moves around, motions faster at higher temperature. So it may be even anything. Maybe even that isn't true. Like you can probably billiard balls on a pool table. You could probably do in labs. So it's called molecular dynamic simulation, but it doesn't have to be molecules. And here it's atomic. It's like atomic dynamics. So it's a pretty open framework. You can do anything you want. And again, like I said, maybe if you looked like billiard balls and LAMMPS simulation, you would find it. How to simulate, yeah. So yes, you can do billiard balls with LAMPS. Okay, so there you go. So you can basically anything you could put in there, and you can find, and the code will be there. So whatever you're doing, you can copy the code, modify it for your thing, and even usually because it's like a club almost. So it's like if you find someone that did something billiard balls like you're interested in, and you email them, they'll come back. Oh yeah, I'll help you, and they can give you clues to like how to do the billiard ball problem. Like what if it was this situation I want to know about, like what if the table was tilted just a little bit, then how do I win billiard balls and simulate it? So you can just find people, it's like a club almost. So once you start doing it, you just email the person that did the other and they'll help you. Anyway, so and we'll do one later on, but that's about it, I guess, I got on this thing. So it's 3-page paper, but it's got a lot of equations. So let's see what I got. So this is important here. So he's talking about homogeneous and classical nucleation theory, which is homogeneous, like nucleation from nothing. You have the liquid, then something just forms, right? But he's doing it at an interface, and that's the classic situation for heterogeneous nucleation. So this is like, what's the difference between those two? Well, I mean, the energy is half as much. I mean, the size of the phase is half as much when you get to, so this R is 1/2 of the homogeneous, and then the energy is significantly lower. Energy barrier is a lot lower for heterogeneous nucleation. So he's not doing a 3D nucleation. So he should really be using this model, not that model. So he kind of ignores that. Then which does the paper discuss? He's discussing homogeneous. And then, which does the paper discuss? That's an open question because he's at an interface. So this means like he's at an interface doing homogeneous nucleation, which sounds a lot like heterogeneous nucleation. So you have to resolve for yourself what the heck's going on with it. Like, is it homogeneous or is it heterogeneous, and does that matter? And then 1A shows the nucleation. Base describe nucleation. The first two terms are from CMT. Explain the first two terms. So one's bulk, one's surface. All right, so his aren't bulk and surface. In the classic, the first one's bulk, and it has R cubed here. And the second one is surface and has R squared. And here he has like R squared, which would be like the second one, and then R. So this looks a lot like the heterogeneous nucleation situation. Right. So notice when you go back for heterogeneous, we have R squared and R. So it's kind of like that. So, but this is a bulk free energy, and that's a surface free energy because it's got T in it also. Right. Whereas in his thing, wherever he is, so he doesn't have this gamma is like calls it like a bulk energy, but it's per unit area. The things are really all kind of confused here. And then this is actually, he calls it interfacial energy, but it's really a line energy. Like there's no, if interface has 2D and this is 1D. It's like gamma is 1D energy. So it's basically looking down on that green boundary. It's the energy of that line that goes around the C line. The energy associated, enthalpic energy associated with the boundary between the two on a line, not on an interface. So it's really a line energy. And then because it's a line, it's got the stresses associated with it. There's some of, like, I probably could have asked about the Laplace, why isn't there a Laplace equation? You know, like a 2D Laplace equation has something to do with, like these stresses are really like the Laplace equation, like the pressure. In 3D would be pressure, and here it's strains, interfacial strain. Anyway, so there's that business. I mean, derivative, let's see, it's bigger. There's derivation of 2 in the supplemental. In the paper, so the paper is weird, like you can't read the paper unless you have the supplemental because he doesn't define new B or R or rho, right? Or F, like those things. So if you go to equation 2, so he just comes up with this. There's equation 2. So there's new R, mu, B, R, and rho. They aren't defined here. Or rho is a coral radius of dislocation. And is B. So that doesn't make sense. Actually, this sentence is kind of weird. But so B is a Burgess vector for the transition for the interface. And then anyway, he doesn't define any of the terms, and even they aren't defined in the supplemental. Maybe they're defined in the supplemental, I'm not sure, but anyway, it's kind of shoddy to do that. Like you should, if you write an equation, you should define the terms right after so people can figure out what you're talking about. And then explain each of these terms used in equation 2. So I think you have to go back to the supplemental and figure out, the supplemental is there and you can figure out like what he's talking about. Does winner include a term that accounts for changes in entropy? So that's kind of a loaded question. So he's got all this free energy, like, you know, the energy has to have entropy and enthalpy in it, right? And if you read the paper, you'll find out that he's dropped off the entropy part. For one thing, his initial simulations are at absolute 0. So this is at 0K. So there's no entropy at 0K. So that's the reason to go to 0K is you can ignore the entropy part. But then later on, he shows, this is a little bit not explained either. Like here he goes to 1500K. So he doesn't exactly explain where he goes from 0K with no entropy to 1500K, but he's still ignoring entropy there because no entropy term in his thing. There's no temperature dependent term in his equation. And right, you could have, like you'd say, like in the Gibbs phase rule, like G has this GV has a temperature that's delta H minus T delta S. There's a T in that, so there's an entropy. But that isn't what he does. He just gets a number for that. So he doesn't get a temperature dependence to this. This is where the temperature dependence, the entropy would be. But what he does is he solves for that number because he can't include entropy in it because he doesn't know how to. So he ignores the entropy part, and he says he can't solve for this number. If you read the paper, there's a lot to it, but basically he can't solve for that number. He can't calculate that number with his what he calls static molecular static calculation. Like a molecular dynamic simulation, molecular static calculation uses those two phrases. So molecular static calculation, you can get this line energy, you can get all these strain energies, but he can't get this guy. And he can also calculate the total energy from his molecular static calculation. So he does the simulation, and then he solves for this, but it's a fixed number, like it doesn't change. He gives that number in the table there. So he gets that from his molecular dynamics simulation. This comes out of it. And because of that, it can't have a temperature dependency. It has no entropy. That's the way I read it. I mean, you might look at it more carefully, but basically, he has no entropy in this at all. So the question, does he have a term that accounts for that? No. And then why not? You'd have to say all that stuff I just said or figure out what you think about it. So these are like a couple things of thinking things here. Like which is a hetero or homogeneous. See, there's not a right answer to these things, you know, but there's a wrong way to do it. I mean, you could say like nothing, but basically if you say something, it's probably going to be okay. But and then and then the similar 2D analysis thing, critical size, carry out the minimization. So just do that yourself. Equation 5 to get 6. So you have to do the derivative, set it equal to 0 for equation 5 with respect to 2, 3, 4, 5. So with respect to the phase size, this L. So you can take the derivative of that with respect to L. And then you should get this. If you so do that, do the derivative of that, set it equal to with respect to L, then set it equal to 0, then solve for L. Right, and then solve for L, and then you should get this for your answer for L. Once you set that derivative to 0, you get that. And then once you can plug that L back into like this equation, get the energy. To use that critical L to get the critical energy, which would be the peak energy in that plot, would be the top number in this plot. So that equation is the yellow lines here. And then the dots are the molecular dynamics simulations. So he gets perfect agreement between the simulations and his theory, his equation, which is another. So there's two kind of things that verify what he's doing. He gets a perfect match here. And then he can show that he actually does get growth at above a certain size and that no growth below a certain size. Right, so those two are this critical energy theory applies to this weird interfacial phase thing. Then that's the free energy nuclear size. What's the difference between the top and bottom? So the top one's a very thin layer and the bottom one's a normal thickness layer. And then comes the nucleus left of the peak, it dissolves. Right at the peak, it grows because the free energy gets smaller as it gets larger to the right of the peak. It's a difference in grain growth for positive and negative values of this energy. It's a difference in terms of free energy, positive. So if you have a negative value, it would have to always be negative to grow the phases, I guess. This is units on the side of this. Nucleation energy. So he does have positive and negative. All right, let's see, how does that work? So you grow it up, and then beyond that point, it's a spontaneous growth. And then before that point, something happens with the nucleation energy goes negative. I don't remember what. That should be the notes. Let's see, maybe Google this. Energy complete means there's no energy buried or becoming new phase form. It's true. So it's already negative. It doesn't matter. Spontaneous rapid nucleation. Spinel decomposition. No active energy, rapid phase change. Okay. Well, I guess that means that I guess somehow you're reaching the spinel regime. That kind of makes sense. It's kind of like, anyway, you get spontaneous growth when this is negative. No matter what, you have drop in free energy when you make the phase, so it's going to just drive the growth no matter what. But over here, on this size, it grows to be larger. because you're lowering the free energy, but it's still positive, so it needs a nucleus to form. So I guess that's nucleation growth and spinal transition. I guess that's what Google says here. It's not exactly the way I remember it. Classical nucleation theory. This is probably in here somewhere. Bulk free energy, Green curve. Yeah, you could look at this too. I should link that. This actually has the whole thing in it. This has the answer to that. We can look at that. I'll post that up. Then how is R measured in these simulations? How's R measured? How is R measured? I don't know what that is. Well, I think you got to read the paper to figure that out. It's not simulation process, critical radius, blah, 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 blah. How's R measured? I'm not sure exactly how R is measured. It's got R here in the energy, so it has to measure R. And R forms on its own. Well, because you have to figure out how R is measured. Computational details. Calculation of Burgess vector. That's it. He says somewhere in here how R is measured. I don't remember. I mean, you'll have to figure it out for that one. I don't remember the answer to that, but anyway, that's about it for this thing. Any questions on this thing or? I mean, it kind of looks like it might not be that bad. There's a lot of equations. If you read the stuff about the Gibbs nucleation theory, and then couple it with that paper, I mean, it should be okay. It's kind of the same thing as those. This is a pretty critical part of thermo for materials, this Gibbs phase growth thing. Anyway, it links into the Gibbs-Thompson equation, and the other things are all kind of based on the same thing. So anyway, that's about it. That's what I got on this thing. That's it for today. Unless you guys have questions about anything. Good luck.